we looked at this result. We've been doing things by first principles so far, right? But we noticed when you do things by first principles, you start to notice some patterns, and mathematics is all about patterns, right? In fact, one of the first derivatives that we looked at, this guy, actually may have been the first one, right? We saw, okay, you take this and you get 2x. If you were to differentiate, find the gradient function of x cubed, you would get 3x squared, and if you did it with x to the 4, you get 4x cubed, right? So we thought surely there's got to be a pattern here, right? If I differentiated, say, x to the 400, please don't make me do that by binomial with first principles, right? Good morning. I should be able to take advantage of something. So we went back to first principles and we developed this rule to say that if you have x to the power of any power, right, any number, then you're going to get this, n x to the n minus 1. I guess what you would say is that power, it comes down out the front, becomes the coefficient, and then you drop down the power by 1, and then voila, all of your results, right? So we've been going through this fairly quickly. Let's just come back to this for a second and just make sure we surround this with the right language, because I've been saying a few things. Some of you have met this language before and some of you haven't. Okay. So first, this guy at the front. I think I alluded to it, but just to make it really formal, this thing is called the differential operator. The differential operator. Just like log or sine or functions like that which require some input, right? So you can't say, for example, log base 2 equals 5, right? Because this log thing is an operator. It's meant to operate on something, right? So you've got to have something in there. Just as much as you've got to have, like 3 times equals 18. There has to be something in there for it to operate on. So it's a differential operator, right? What this specific differential operator means is, this one is differentiate, and because there is an x down the bottom here, an x, so it's d on dx, right? It means differentiate with respect to, as in the variable you should be looking at and applying this kind of rule to, the variable you're after is x, okay? Now, differentiate with respect to x, this with respect to comes up so often, you'll often see it abbreviated as WRT, with respect to. Yeah, you'll need to catch up a little bit. You can see I could apply this same process to anything like with a different set of letters. It's just a label. It's just a label, right? So you might see, for instance, d on dt, right? Differentiate with respect to t, and that often is like time. So if you have something like, sine t, okay, you'll meet that soon enough. You can differentiate with respect to any variable. For example, you could differentiate with respect to r, right? Now, this, let's just think about this, right? Just imagine it's an x. Just imagine, right? So what you're going to do is you're going to pull that power out the front. That's a 2. There's a pi just hanging out there. It's just another number. And then you're going to bring the power down by 1, right? So it was 2 before. So now it'll be 1. And that should make you really, really suspicious. We'll come back to that result in time. Okay. So this is a differential operator. Because there's an x down there, it means differentiate with respect to x. And because it's an operator, there has to be something in here. Okay, there has to be something in here. So this is your function, right? This is the function being differentiated. Once you differentiate it, right? Excuse me. What you get over here, this result, this is called our derivative. I've thrown this word in there before, the derivative. It just means, it literally means, it comes from something else, right? It came from this original function, you differentiated it, and then you end up with the derivative. We introduce this idea as it gives you the gradient, right? So it's also called the gradient function. They're just different names for the same thing. Okay? the gradient function, if you have some point like x equals 1, and you want to know what is the gradient of this at x equals 1, you put x equals 1 into the gradient function. Okay. Very, very important. This is differentiating powers of x. Okay. So this process, using the differential operator and getting the derivative, even though it's called the derivative, this is not. I will throw sharp implements at you if you say this process is deriving. It's not deriving, it's differentiating. And that's why the title is what it is. And why, if you ever hear me talking about trying to tell the difference between two things, I always say distinguish, not differentiate between those two things, because in my head, that's what differentiating is. Okay? So, these are all of the words. You'll hear me use them interchangeably. Here, find the derivative of this. Let's find the gradient function. Let's evaluate the gradient at such and such a point. This is what we're referring to. Okay, so that's what we looked at last time. Let's now think about this. There are lots of things that you can extend this to, okay? You can extend this to regular old ordinary powers, okay? But what about, for instance, if I differentiate a number, like 3 or 4 or 5 or 600, right? I'm just going to class them all as C, as in constant numbers, okay? So if C is just some real number, okay, what will the derivative of this real number be? Yeah, it's just going to be 0. Now you can see this from two different points of view, okay? Firstly, you can see it as the fact that a constant is really a power of x in disguise, is it not? Okay, so it's x to the 0, right? So it kind of, when you have x to the 0, constant times x to the 0, okay? What happens to that 0? Well, it's going to, first thing, come out the front, so it'll be 0, x to the, and then it doesn't actually matter what I do after that because I'm multiplying by 0, right? So therefore, that just disappears. It's just going to be 0. Now, there's another way you can see this. Do a really, really quick sketch for me underneath here. Because we are doing more than just algebra, right? Just applying algorithms to this. We're trying to work out the gradient of this thing. Well, what does a function look like if it's just equal to a constant, right? If I have, say, like, you know, f of x or y equals 5. What does that look like? What kind of graph does it describe? Y equals 5. That sounds to me like it's a horizontal line, right? I mean, that's what I was going to say next, right? So you've got some kind of horizontal line here. Now the gradient of a horizontal line, gradient is rise over run. How much is this thing rising? Answer, it's not rising at all. Okay, it has a gradient of 0. Okay, so we get this result by applying our rule, which we got from first principles, but also from just thinking about what is this actually doing? It's finding the gradient of a horizontal line, which is 0.